Question number 6.287. A gold foil of mass m is equals to 0.20 gram was irradiated during time t equals to 6.0 hours by a thermal neutron flux falling normally on the surface, and following the t equals to 12 hours after the completion of irradiation of the activity, the foil became equals to A 1.9 into 10 to power 7 disintegration per second after this activity, after the irradiation. Okay, let me mention here, it is after irradiation. Okay, now see, find the neutron flux density if the effective cross-section formation for a radioactive nucleus is, this cross-section for the radioactive nucleus, sigma is equals to 96 and half-life is equals to 2.7 days. Here we have to find out proton flux density. Okay, so let's consider that how this process would take place. First, this neutron flux will fall on the golden foil on this particular cross section, and due to that some energy is being provided. Okay, and simultaneously some nucleus will be generated and some radioactive decay would also take place. Okay, so we can say the rate of nuclear generation will be equals to rate of supply minus rate of disintegration, right? And we already derived the relation in previous questions. From there we can directly write that n is equals to q over lambda 1 minus e to power minus lambda t. This equation is already derived. Okay. Now see, so here first we must have information about this q. Okay, for that purpose cross-sectional area is given. Let's take density is j and suppose there are n number of molecules. Okay, so from there we can write q is equals to nj sigma. Okay, before that it would be better if we'll calculate number of host molecules in this gold foil. Okay, so for that purpose first of all we have to calculate number of moles. Okay, so moles is given mass 0.2 divided by mass number of gold, that is 197, I think 197. Okay, so this n is equals to number of mole 0.2 over 197 into Avogadro number 6.023 into 10 to power 23. Okay, which is equals to 6.11 into 10 to power 20. Okay, this is number of host nucleus. Okay. So now we can rewrite this expression as n is equals to nj sigma upon lambda into e to power minus lambda t. Right? Now see, this lambda can be written in terms of half-life, or later on we can write this, and we can calculate this activity A, which is given after 12 hours we are getting this much amount, right? So we can write A is equals to dn over dt now when irradiation stops. So if we'll differentiate this expression from there, then we'll get A is equals to nj sigma over lambda into 1 minus e to power minus lambda t into lambda into e to power minus lambda t. Right? So from here we can figure out j, that j is equals to A into e to power minus lambda into t, this term. Okay, this is for this will get, okay, Okay, let me rewrite again. So this is in multiplication. Okay, please take care. This lambda and lambda would get cancelled out, right? So from here we can write A is equals to nj sigma into 1 minus e to power minus lambda t into e to power minus lambda t. So if we'll rearrange this expression, then we'll get j is equals to a into e to power lambda t divided by n sigma into 1 minus e to power minus lambda t. Right? Just simple mathematics. Now see, this lambda, we have information that this activity disintegration per second is given when t is equals to 12 hours. Okay, so we can replace this t by 12 hours and a by 1.9 into 10 to the power 7. And along with that, if half-life is known 2.7 days, okay, so we can convert this 2.7 days into hours and we can calculate lambda. Lambda is ln2 upon t half. So from here we can write this j is equals to a into e to power minus ln2 upon t half into tau, which is given there, divided by n into sigma into 1 minus e to power minus ln2 upon t half into tau. Okay, so now all these values are known. A is given 1.9 into 10 to the power 7. T half is given 2.7 days, that is 2.7 into 24 in terms of hours and into 3600 if we want in terms of second, although all the units are given in hours, so we can take it. Okay. Now next, this time is 12 into 3600. This tau can be replaced as, and A is equals to already given, and we have calculated 6.11 into 10 to the power 20. Sigma is given 96 centimeter square. So we will substitute all these numeric values. We will get J equals to 5.9 into 10 to the power 9 proton per centimeter square per second.